In this demo, we learn how to fine-tune the weights of existing pre-trained neural network models to solve problems of specific interest. In order to motivate why we are looking at this kind of problem, recall that modern deep convolutional neural networks tend to have tens, if not hundreds of layers. And in all, they have millions, if not tens of millions of parameters that can be trained. More often than not, deep convolutional neural networks also have skip connections. And in fact, the residual network or ResNet family of models are an example of such architectures. So in order to train such massive deep neural network models, we also require a tremendous amount of training data. And in many practical applications, such large, massive data sets are simply not available. It's not typical to have, a data set with 100 million examples. More often than not, we'll have maybe a few hundred or a few thousand examples. Even that can be a challenge to gather and curate. So what does one do in this setting of limited data? One possible solution is to start with a deep neural network architecture, which has been initialized with a good set of weights, maybe pre-trained over a much larger existing data set. And then take that architecture and fine-tune those the network weights for the particular data set that you're interested in. Okay, so this is actually a very fruitful approach. And as we'll see, this can be used to solve many interesting kinds of problems. So in this demo, we'll solve a simple classification problem of classifying dog images versus cat images using a very, very small training data set. This training data set consists of 30 cat and 30 dog images, so really, really tiny, and maybe a test data set of what 12 images each. I have provided the images as a zip file, and you can download it and place it anywhere. I placed it in my Google Drive folder in this particular path. Okay, so let's take that data set, and we'll use this very, very tiny data set to train a dog versus cat classifier. Okay, so the way we'll do this is, so I have this some boilerplate code to load Torch and load the data sets. So the way we'll do it is load an existing pre-trained model. Torch Vision has a bunch of models already present, so we'll just pick one of them. For this demo, we'll pick what's called a ResNet 34 model. So ResNet 34 is, as the name suggests, residual network, 34 layers. So let's just load that, and we will load it. We'll load not just the architecture, but also the weights. So this particular model has been it's been used several times in the literature before. It is a model trained on the well-known ImageNet dataset, which consists of several millions of images and 1,000 classes. So it's a really big model. So let's examine its structure. So I can just print the model and see how it looks. So as you can see, the model is very big. As the name suggests, it has 34 layers. So let's count them. So as you can see, there are multiple convolutional layers. The building block of a ResNet model is a pair of convolutional layers with a skip connection, right? So this is so there's a skip connection from input to output of this block, and now we have pieced together several such blocks. Okay, so there are multiple such blocks, each of them with a pair of conv layers, and there are batch normalization and ReLUs thrown in the middle for the nonlinearities. Many such blocks, you can sit and count them. There are 34 overall. Most of them have several channels, hundreds of channels, both input and output. And finally, after all the residual blocks, there is a pooling followed by a linear layer. The linear layer basically collapses all the features and produces 1,000 output. So the 1,000 output neurons corresponding to 1,000 classes. Okay, so this is a very, very big model. In fact, it may be fruitful to quickly count how many parameters there are in this model. So let's just build a simple routine which will count the parameters, right? So this will just simply sum up all the trainable parameters. Okay, so if P is a model parameter, which supports a gradient, right? Which supports a gradient. Okay, so as you can see, there's approximately 21 million parameters. So that's a heck of a lot. It's a lot. So let's see. I mean, so training ResNet 34 from scratch on our tiny image data set of 60 images is kind of going to be pointless. So we will not train everything from scratch. Instead, we'll only train, we'll only fine tune all the weights, all the existing weights. So first, what we'll have to do is to change the number of output classes. So this is so what we're going to do now is a binary classification problem. So let's just redefine the fully connected layer. So fully connected layer is model.fc, right? So it has 512 input features and 1000 output classes. So I'm going to just redefine this using nn.linear, right? So this so I'm going to redefine it to have 2 output classes because we are now interested in a binary classification. So what nn.linear would do is to initialize the last layer, is to set up 512 times 2 last layer and initialize them to random weights. Okay. So now if we examine the model after we redefine the last layer, it's the same architecture, except that now the last layer has been redefined, right? So it's now suitable for binary classification. Okay. Good. Actually, let's quickly do a model evaluation to see if the new model that we defined can actually do classification for our existing data set. So I'm going to just write a quick script. So above, in the beginning, we already loaded the data set, and there are 2 data loaders, one for the training data and one for the test data. So let's just evaluate the model and the test data and see how well we do. This is probably not going to do very well because the last layer has been randomly initialized, and really the ImageNet is a different data set, so it's not really appropriate for our particular cat versus dog classifier data set that we have right now. So let's just quickly evaluate this newly defined model and see how well we do. So I'm going to step through the images of the test data set. So I'm just make sure that we don't update any weights at this stage. So I'm going to set grad enabled equals false. Let's just use the current model to predict the labels. This is not going to be helpful, but let's just see what happens, right? So the outputs are the output logits, and I need to extract the classes, and this is just the max logit. Okay, that's about it. So let's count how many labels we got correct. Just the sum of what we predict. Does it actually match the true labels? Okay. And after we do that, we'll just print the percentage of correctly classified images in the test data set. So that's just data loaders of test data set. Okay. This is on this. See how well we do. See how well we do. Hopefully it doesn't throw any errors. As you can see, we got about half right. This is exactly what we expect because it's a binary classification problem with random weights. So you would expect that you do no better than chance, which is 50%. It's great. Cool. So that's fine. So all we need to do now is to take this new model that we've defined and fine tune its weights for our particular data set. And the rest is basically routine. We've seen this many times before. We define a criterion. It will be the cross entropy loss because we're doing classification. And we also define an optimizer for this particular model. In general, for ResNet type models equipped with batch norm, SGD is a very good choice. So let's just use SGD with a small learning rate. And we'll also throw in some momentum for fun. Okay, so if you want to refresh your knowledge of momentum and learning rate and choice optimizers and so on, I'll link to the appropriate demo which we discussed earlier in this class. That's basically it. So this is all I need. The rest is just now routine. So I'm just going to, you can pick. So we've done this many times before. So I'm just going to repeat the code that we have written before and train the model for a small number of epochs. Okay, so this is just boilerplate code from before, but just trains the model for 5 epochs, and at the end of each epoch measures the loss as well as the accuracy for both the train and test data sets and just keeps track of how we're doing. So let's just run this. So we start with about 50% accuracy, and as you can see, within 5 epochs we should be able to do really well. That's it, we're done. So we trained the model for 5 epochs, and as you can see, we started at lowish accuracy of about 50-odd%, but then within a couple of epochs, both the train and the test accuracy have gone to 100%. And if you want to visualize it in a slightly different way, we can just plot it. And there you go. Cool. So here, in fact, the test accuracy is slightly higher than the train accuracy, which is not typical, but for such small data sets, it can happen. Right. So there you go. So this is a very simple example of fine-tuning an existing deep convolutional neural network model for particular problem having a limited number of data. Feel free to use this idea to try it on your own data set. For example, what would happen if you have a slightly larger data set of, say, 100 or maybe a few hundred images? What kind of behavior would you expect to see? What kind of architecture would you want to start with? Whether you start with the ResNet 34 or something bigger or smaller. So these are all design choices that you can make.